Okay, here's some questions from 2001 from the VCE physics exam back then, dealing with some orbiting space stations and spacecraft, and I found some old videos to save my voice and re-explaining it again. I'm just going to play these, so here we go. Okay, we're going to look at the question from 2001, question 1 firstly. Just reading through the text there. The MIR, the Mir space station, orbited Earth at an altitude of 390 kilometres. From that you'll be able to work out a radius. So it's going to equal 390 kilometres, and that's the altitude of 390 kilometres. So you need to add that onto the radius of the Earth. And the radius of the Earth, if I look back in my notes, is 6.4 by 10 to the 6 metres. So you'd need to add those together carefully. I'm just grabbing my little calculator out here to do the calculation. 390,000 plus 6.4 divided by 10 to the power of 6, which gives you 6.79 by 10 to the 6 metres as the radius of orbit for the space station. Okay, that's how you interpret that bit of information there. The total mass of the space station was 140 tonnes, so we know that we've got an M equals 140,000 kilograms. And Mir completed 83,500 orbits in 14.6 years before it crashed. So the first one that we have to do here is to calculate the period of Mir's orbit in seconds. So in order to do that, we have to work out what the time for one orbit is. The period T will be equal to the total time divided by the number of orbits. So in this case here, it's 14.6 years times by 365, just use 365 days for the number of years, times by 24 hours, times by 60 minutes, times by 60 seconds. And we need to divide that all by the number of orbits, which we're told in the question was 83,500. And if you plug that into your calculator, you should get an answer of 5.514 by 10 to the 3 seconds. Okay, which can be rounded off to 5.5 by 10 to the 3 seconds. So that's how you do the first one. Then to calculate the speed of Mir while it's in orbit, what we need to do is, I'll just change that, that's question 2 now. Oops. Question 2. The speed or the velocity v is equal to 2 pi r, which is the distance of one orbit, divided by t, excuse me, which will be equal to 2 pi times, we've already worked out the radius at the top there, 6.79 by 10 to the 6 metres, and we need to divide that by the period, which we got 5.514 by 10 to the 3. Plug that into your calculator, and that should give you an answer of 7.7 by 10 to the 3 metres per second. And that's how you would do question 1 and 2 from the 2001 paper. Something that's probably important for you to keep in mind is that when doing calculations like this, it can be useful to put brackets down the bottom there. So many times I've seen students multiply everything in the top, then they go divide by 5.514, and then they go times by 10 to the 3. And the calculator just throws, it sort of does divide by 5.514, and then within itself goes equals, and then it times the answer by 10 to the power of 3, which gives you a much different answer. So brackets down the bottom there are generally pretty useful. Let's move on to question 3 and 4. Okay, now looking at question 3 from the 2001 paper, and this one continues on from the previous question. Calculate the value of the gravitational field strength at 390 kilometres above the Earth's surface. So we did previously work out that the radius of the orbit was 6.79 by 10 to the 6 metres. So that comes in fairly handy for that one there. To work out the gravitational field strength, that's a G, which is just the acceleration A, is equal to V squared over R. And we worked out the speed previously at being 7.7 by 10 to the 3 metres per second, divided by 6.79 metres. Now remembering we have to square the top line, important that you do that. And we plug that into the calculator, and that should give you a value of 8.78 newtons per kilogram, which is the size of gravity up there. Moving on to question 4. And that says, when Mir was in stable orbit, an object of mass 2.5 kilograms was placed on a spring balance that was attached to the inside of the space station. So what would be the weight shown on the spring balance? Explain your reasoning and show your working for determining the reading of the spring balance. Now, if it's been attached to the space station on Mir, the space station is in constant freefall. The mass would also be in constant freefall as it travels around the Earth. So therefore there should be a zero net reaction force between the two of them, because they're both falling at the same rate, and that's what's happening with a stable circular orbit. Everything is travelling at the same speed, everything is travelling at the same rate towards the centre of the Earth, so it's in constant freefall. So therefore the normal reaction force from the spring balance should be zero. So zero is what you get. If you were going to do a reaction force, the net force would be equal to mg minus the tension in the spring. Must be equal to ma. The acceleration is equal to gravity, so the tension is going to be equal to zero. Excuse me, so you have a net force is equal to zero, the tension is equal to zero. Mass times gravity will also be equal to that as well. So we've worked out gravity previously, so in this case here the tension has to be equal to zero. Yeah, so this is one of those ones, because everything's in constant free fall, there's not going to be any reaction force between the spring and the space station, wherever it's been attached within the space station, and you'll get a tension in the spring balance of equal to 0. I'd just better finish off this calculation here for you. So F net equals mg take away T. T will be equal to F net minus mg. The net force is ma, and in this case here the acceleration is also that it's experiencing from the net force will be equal to gravity. So in this case here we have A equals G. So that means ma take away mg is equal to 0, so therefore T is equal to 0. That's that calculation. Okay. Okay, continuing from the 2001 questions. This one's question 5. Question 5, 6 and 7 all relate to a new thread, which says on the 12th of February 2001, spacecraft named the Near Shoemaker landed on Eros, a peanut-shaped asteroid between the orbits of Earth and Mars. The 450 kilogram spacecraft had a weight of 2.5 newtons when it landed on the asteroid. So for question 5 it says to calculate the weight of this spacecraft on the surface of the Earth. So fairly straightforward, weight is equal to mass times gravitational field strength. The mass is 450 kilograms times by, we allow 10, we could use 9.8, so 4500 newtons of weight. The answers that you've been provided with there use 9.8 instead of 10, which is where the 4.4 by 10 to the 3 comes from. Just remember to have a look on the front of your exam paper. It should say that 10 is acceptable. If you can't use 10, you need to use 9.8. So for that same calculation again, using 9.8, 450 times by 9.8, and that will be equal to 4410 newtons. And that's question 5. So for question 6, reading through the thread for question 6. Before landing on Eros, the spacecraft orbited at a radius of 50 kilometres from the centre of mass of Eros, with a period of 5.9 by 10 to the 4 seconds, which is around 16 hours. Find the mass of the asteroid from this information. So what you need to do with that is derive it. We're going to go through a derivation of an equation. And this will be something that will come in handy for your cheat sheet for the exam. It's one of the equations that's been given to you, but we also know that V is equal to 2 pi over 2 pi r over t. So what we're going to do is substitute that V into there. So that means that this will be equal to m over r times by 2 pi r over t all squared, which is equal to 2 squared is 4, m pi squared r squared over r t squared. And we can cancel down one of those with that. So that gives us the equation G is equal to 4 pi squared m over t squared. That's a ratio that can be used a little bit. Then we can also cancel a few things down from there as well and rearrange stuff. I've left out the r from that equation. So then we can cancel things down, so we've got an m on both sides that we can cancel down. If we multiply both sides by r squared, we basically bring that r squared over to the other side there. So just as the intermediate step in there, we now have g with a big M will be equal to 4 pi squared r cubed over t squared. And then we'll divide both sides by the g, which gives us m is equal to 4 pi over g t squared. Okay, now you've got that equation down the bottom there. That'll be a handy equation for you to hang on to. I'm just going to fix up that 2. So that should be 4 pi squared r cubed over gt squared. Now to actually work out the question, you can come back to that derivation, and I'm just going to rub it all out. Look how it magically disappears there. So I just want to keep that equation in the corner there because that's what we're going to use. And if this is on your cheat sheet as a derived equation, that's all you would need. So I can get rid of that bit as well. And I'll put an orange box around that. So that's something that you can add later. So to calculate, question 6, to calculate the mass of Eros equals 4 pi squared r cubed all over g t squared, which is equal to 4 pi squared times by the radius. And the question tells us that it's orbiting at 50 kilometres, so that's times by 50 by 10 to the 3, so it has to do it in metres, all cubed, divided by gravitational field strength, the constant, we have 6.67. And that needs to be multiplied by 5.9 by 10 to the 4 seconds squared. And if we plug that all into a calculator, we need to get the answer of 2.12 by 10 to the power of 16. And that will be an answer in kilograms. Now you may notice with the notes that there was a answer of 6.67 by 10 to the 15 kilograms given. The difference there is that they didn't square pi when they were completing the answer, so I might have to send him an email to fix that up for next year. So that's that question there. Now to continue on, 2001 question 7. This one here has a diagram which is provided, so it's got a little picture of Eros, and it's got the direction of motion going that direction. And it's got a little picture of the spacecraft there. And there is a very clear thing that says not to scale, obviously. What's that error can spell? And it says draw one or more labelled arrows to show any force acting on the spacecraft as it orbits Eros. You can ignore any other astronomical bodies. Now you should know that anything travelling in a uniform circle, the forces, the net forces acting will be towards the centre of the circle. There has been times that labelling it net force hasn't been acceptable, so you could have called that a weight force acting towards the centre. If you had just drawn the arrow but not actually labelled it, in this case here you're not actually answering the full question because it says draw one or more labelled arrows. Labelled arrows. Labelled arrows. And that's an arrow with a label. So you could have had weight force, or you could have had gravitational force, you could have had mg, or you could have had F subscript G like that. Any one of those would have been acceptable. And yeah, that's how you had to answer question 7 from 2001.